And welcome back to Multi-Threaded Engines. This will be part 3 where we talk about how to design an architecture, software architecture to leverage these multiple threads. But wait, you say, you didn't tell us how to create a thread. It's true, I haven't mentioned that yet. In C++, you actually have several options for how to do it. Used to be it was not part of the C standard library, so Windows and other operating systems would provide an API that you would use. There was also a pthreads, a platform independent library, very available, and you see that a lot, but it's older and uses a C style API. Now that C++11 has really made some penetration and gotten out there, now that C++11 has found official favor in video game use, we can use the standard built-in std::thread. It's a good choice. It's a cross-platform built-in standard API. And I would recommend that's what we should use for and that's what we will be using in our labs. All of these are the same idea though. All it is you say, but all of these work basically the same way. All you do is say, I have a function that I want to kick off on another thread. That's what happens. You say, hey, start a new thread and start it running this function. So you'll have some way to pass in the function you want to run on that other thread, and then off it goes. Wiggle. Now that we have multiple threads running at the same time, we can think of them as running in parallel. So we have two threads running down parallel tracks. Okay, so how do we decide what program to put on what track? There are two main ways we split things up. The first and perhaps most obvious way of thinking is to take two different tasks and divide them onto the two different threads. That's very easy to conceptualize, but it turns out maybe not the best way to scale up to a large number of threads. The other way to look at things is instead of splitting the job up task by task, we might split it up in terms of data, where all the threads will be doing the same task, just operating on different parts of the data. And honestly, this was always a lot harder for me to conceptualize this, but it scales much, much better. Let's take a look at this. Here's what task parallelism might look like. Let's say we're going to split our engine into a main thread and a rendering thread. And so over there we've got the main thread, and it's doing all the things you think of that isn't rendering. So we're going to start by getting some input, running our updates, whatever they are. We got the animation, the physics, yada, 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 all of this stuff. And on the other thread up here, let's run all of the rendering type of stuff. So maybe we'll do a frustum call. We'll talk about that later. Remember alpha, we need to sort back to front with alpha objects. So maybe we'll do that sorting there, or maybe we'll want to sort by material for the opaque objects. So we'll do that and submit the primitives and do all the post-processing and yada, yada, yada. We'll do all of that on a separate thread. So that'll allow us to run these in parallel at the same time, theoretically. We will have to be pretty fancy about it because you'll notice these things are moving the objects. These are going to be rendering the objects, and yeah, that's going to involve some double buffering of data, but we could pull it off. We can do this. And in fact, modern engines, game engines, do this. I was just saying, it would be better, instead of doing task parallelism, it would be better to do data parallelism. But we do tend to, this is well established as a technique. We tend to see this a lot. Now, there is a problem with this, and we saw the same thing with the double buffering of the display. When we did that, we introduced a frame of lag into the responsiveness of the game, and now we just introduced another frame of lag, because while the current thread, the update thread, is getting your input and responding to your input, it has to finish the current frame before it starts rendering that frame, and then when that's finished, the GPU can start actually drawing. So we've actually, by doing this, we've introduced a frame of lag. Now, what does that look like? You can see here, if you may have to zoom way in. I would say open up the PDF so that you can zoom in on this image and get a better view of exactly what we're seeing here. But on this frame right here, we can see the user. You can see the user's finger is in motion. The user has pulled the trigger on the controller here on frame 0. And then we watch the frames as they tick, 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 looking for where does that muzzle flash appear on the gun. This is a gun that the user is playing. This is from Grand Theft Auto 4. And it took from frame 0 all the way to frame 12 before the gun actually fired. Well, that's a very long amount of lag. Honestly, no, you cannot account for all that much lag just with this multi-threaded concept. There's something more than that going on in this case. I suspect that this was probably an online game and they built in some lag on purpose so that when you play online, it would feel the same as when you're not playing online. So I've seen that done before, and that would be my first guess. But that's what lag is. When we say lag, that's what that means. Yeah. Okay, so there's another problem with this concept, and that is the chain is only as strong as the weakest link, and the game is only as fast as its slowest thread. So in this example, let's say the game thread is running in 33 milliseconds per frame, but the rendering thread takes 50 milliseconds per thread. That means your game takes 50 milliseconds per frame, and if this was running on 2 cores, this other core is spending a big chunk of its time just waiting. There's nothing to do on that thread. In the profiling lecture, I showed an example of this. This is a very genuine problem if you think of things in this way. Okay, so we saw making a main thread and a rendering thread, but we've got more cores. How do we scale this up? Well, how about an animation thread and a physics thread? And we can just keep on going using a technique like this. But what you tend to get is lots of downtime between the threads because of the interactions between the different steps. I mean, for example, we can't really do pose blending in animation. We can't blend between 2 poses until we decide what poses we want to show. And we can't really maybe do our physics simulation until we've finished our animation. If the animation, it moves your arm, then the arm might bump into the wall, and that will cause the physics to be modified. So we can't run them. We just really cannot run them at the same time. That's kind of the problem. So in that example, the best we could do was to get our animation and our physics thread running maybe 50% of the time, but there was some overlap, so we can't even let them share the same resources. And most of our work is still happening on the main thread and the rendering thread. It doesn't scale to a lot of cores very well. Instead, if we think of our program as a series of steps we operate over several objects, we can split things across cores much more effectively. Using a simple fork and join illustration, we might take, for example, let's consider that idea of pose blending. We're in the animation system and we're going to blend between two poses. We got the run cycle and the idle, and we're going to blend in between them by some amount, right? So that doesn't just happen for one character. We'll have lots of characters. And this is what we're specifically going to do in our lab here in the class. We're going to take one character and put it on this thread, and another character on this thread, another character on this thread. We'll fork off a bunch of threads to run a pose blend on each one of those, and then when they're done, we'll join back into single threaded mode. So this is what's called fork and join. We fork into many threads, wait until they're all done, and then join back into a single thread. So let's see what that might look like. So for example, we're going to do some kind of updates. We're going to decide what every character is playing in their animation, and then we'll fork off into some other cores to do the pose blending. And while the blending is going on, our main core will sleep, and then we'll come back over here, and then we'll do some more single threaded work, and the other cores sleep while that's going on, and then as soon we got maybe something else, maybe the physics system can be split across multiple cores, and we'll do that here. Okay, but see, as you can see, it's still quite difficult to get good utilization on all the cores. We're having to sleep a lot during this. And so that's the big downside of a fork and join style. Instead, let me introduce the concept we call a job architecture. Now, in a job architecture, it is very similar to a fork and join, only we fork the threads right at the beginning of the game. We kick off a bunch of threads running what's called a worker. A worker thread just does any program that you give it, and we'll call that little program a job. What this allows us to do is think a little bit differently. We now can take that thing, for example, that pose blend. We have some poses that we kick off here. Maybe these are poses, so we'll just kick off some jobs, boom, boom, and then we move on with the next thing we can do right away without waiting. Now we'll still get some waits that happen in here, but the idea is that if there's anything else that we can fit into that wait, we'll kick that off as a job as well and try to fill in those gaps. And it allows us to just be very willy-nilly with what we throw onto those threads. So what is a job? Let's take a look at the simplest possible description of what a job might be. A job is simply a function to do and some data to operate on. Now this syntax, this is the C style syntax for a function pointer. Let's take a little bit of an aside here, a bit of a tangent to describe exactly how that works. What I'm saying here is I have a variable of type void, but it isn't just a void. If we look at read from the parentheses, it is a pointer called m function. Inside the parentheses, it's a pointer called m function. It's a pointer to what? It's a pointer to, step outside the parentheses now, and we see it's a pointer to, these parentheses indicate it's a function, right? Like symbol name parentheses is C for that's a function. So I have a pointer called m function. It points to a function. What kind of function? A function that takes one argument, that is a void pointer itself, and this function returns type void. So that's how we read that. That is a pointer to a function. Still on the tangent, remember that a function is just some address in the code that we want to jump to, right? To run a function, you push some stuff on the stack, and then you jump to an address. And that address is where that function is. That address can be a pointer, right? So that's all this is saying. So just take the address of a function, I'm going to stick it here, and I'm allowing to pass in one void star argument into this function, and here it is. It'll be called data. So this is a C style implementation, very old school implementation of what a job might be. Okay, next thing up, we're going to need a queue of jobs. We don't have just one job, we have a whole list of jobs, a queue, if you will, like a first in, first out kind of do them in order, more or less, queue of jobs that need to get done. Workers will simply grab whatever's at the front of the queue and do that job. And when that job is done, they will go back to the queue, grab the next available job. And by doing this, we don't worry so much about are all the threads doing the same thing at the same time. No, we don't really worry about that so much. Instead, we just say, this is all the stuff that needs to get done. Get at it and do it as fast as you can. Okay. So jobs is pretty much the standard way multi-threading is accomplished these days. We still see the render thread and the main thread. So we'll still have your main thread, we'll have your render thread, and then we'll have a whole bunch of worker threads that will do just whatever small jobs you can kick off to them. And the more you can split up your main thread and or your render thread into these jobs, the more you can spread out across the whole machine and make maximum use of your available cores. Now, this does require some thinking to plan how some things are dependent on the order that they run. For example, we mentioned maybe you can't do the physics until the animation is completed. So what you'd have to do is kick off a bunch of animation jobs, and then you kick off a bunch of physics jobs, but you have to make your job manager a little bit more complicated. You have to make it smart enough to realize that it can't start the physics jobs until all those animation jobs are finished. So a modern job manager system, more complicated than what we're going to do in the lab. A real job manager will have dependency connections between the jobs so that if the next available job is a physics job and it can't run that yet because maybe the animation is still going, it'll look down the queue for something else that it can run now. Maybe there's some other job coming up down the queue that is not blocked by animation that it can jump onto right now. That's what we try to do in a real job system. In the labs, we'll just be doing the one thing with no real dependencies. Some examples, real world examples of things that will be found on jobs. Cloth physics is very easy to simulate on a job because it doesn't really tend to interact with other things besides itself. So you can put that on a job. You can even split multiple parts of the same cloth onto multiple jobs. Culling, visibility culling, we'll spend some time talking about that in a future lecture. That's just saying, hey, can I see this object? Can I see that object? Can I see that object? We can split that off into some jobs. Collision detection, obviously, hey, do these things touch? How about those things? How about those things? You can make those jobs. Animations, that's what we'll be doing in our job lab. We'll be doing our animation calculations in jobs. Okay, and like another one that I just threw in here is on the old PS3 hardware, we used to have good cores, lots of specialized cores, and not a very powerful GPU. So we would do skinning as jobs, for example. And I still see skinning as jobs as options in engines today. Like in Unity, I see that option sitting there. Okay, this last thing just says waiting for job completion needs to be minimized. The whole point is to maximize how hard the CPUs are working so that there's no downtime, because that's how we get the maximum speed out of it. And so that would mean putting things in the order that they need to get done and avoiding things that wait on other things. For our lab in our class, we're going to keep things very simple and not worry about these issues. This slide talks about the more advanced topics that you would need to deal with in a real game engine. Just for simplicity, won't be implementing these things for our lab. These are things that you need to deal with in real life. For example, the worker thread. When the worker thread runs out of tasks to do, now what? The worker would say, hey, give me a job. No, nothing, give me a job. No, nothing, give me a job. And I just sit there asking, give me a job, give me a job, give me a job, give me a job. And that occupies that core of the CPU during that time. We might be nice and release that resource for something else to use when there are no jobs. How could we do that? The best way to do it is with some kind of event where the worker thread, when it detects there are no more jobs, it goes to sleep, releases that core for the operating system to use for something else. And when we insert a new job into the queue, we'll send an event that will wake up that sleeping worker at that time. So automatically, we don't need to have it keep automatically waking up on its own. It can be told to wake up when there's something to do. So that's something we would do. Another hidden inefficiency built into the system is that job queue itself. Now, we could have thousands of jobs in the queue. Those all have to be pushed into the queue. Many of them will come from the main thread. Some of them may actually come from other jobs, which happen on other threads. And certainly all the workers are needing to access this job queue over and over again. Give me the next job, give me the next job. We can't have two workers grab the same job. That would really be bad. So we have a shared resource here. We're going to need to protect that. And in our labs, we're just going to put a mutex on it and call it a day. But the mutex can be slow. So there's a technique called a lock-free queue that we would want to do if this was a real game engine. So what is a lock-free queue? A lock-free queue is a queue that is thread safe without specific locks around it. So how does it work? We make use of those compare and exchange instructions that I was showing you earlier to implement all the functions that are associated with a queue without having to add specific mutexes around this thing. We'll use atomic data elements and those compare and exchanges to see whether to make sure that when you try to insert into the queue, nothing else is operating on it right now. And when you try and pop from a queue, nothing else is operating on it right now. This is beyond the scope of this class. It's a whole category of lock-free programming. It's a specialty in programming. And there are lock-free versions of linked lists and a queue and stack and that kind of thing. All those basic data structures that you've learned to create, you could learn to create a lock-free version of that. And here's a link that you can go to. Out of scope of this class, but really interesting type of programming. To wrap things up, I just wanted to show a little bit of some slides from Insomniac Games. This was from some of their early PS3 work when they did their first PS3 game, Resistance: Fall of Man. They relied very heavily on the main CPU in an almost single-threaded environment. to their second iteration of that game, they managed to set up a job system and use it much more effectively. And you can see how much more effectively they're using it with this visualization here. The trick that you see in all of it is this keyword here, deferred. Really, the key to being able to split things off into jobs effectively and get them off of your main thread is to not wait for the answer to a function. If you need the result of a function call, like as a return value or something, that cannot be put onto another thread. But if instead you can say, hey, I'm going to want this answer later, go do the work now, and then later on I'm going to ask you for that result. That allows you to split things off into jobs and make use of the multi-threaded environment. It's a much more complicated way of thinking, but you can get a lot of mileage out of that. Let me give you a simple example. Let's say a raycast. For example, an enemy wants to ask, hey, can I see the player from here? I'm going to need to do a raycast through the environment to see if anything blocks my line of sight. Very simple thing to do. So how you might write that in a single player, in a single threaded environment, you might just say in your AI code, if line of sight to player, then set state alert, else set state patrol, right? So you would do something like that. But thinking in deferred, what you'd do instead is you'd say first in the current frame, you'd say, do the line of sight check. And then you'd go on and do the rest of your stuff, assuming whatever. And then on the following frame, you'd say, hey, give me the result of my line of sight check. Could I see the player? If I saw the player, then I go into alert state. If I did not see the player, then I go into patrol state. And then on the next line, you'd say, and fire off a raycast that I'll be asking you about on the following frame. So you can do that. You can even do it in like multiple stages within the single frame, but it turns out a lot of times you just don't need those results right away, and you can instead sort of defer them for later. So that's the end of the lecture on multi-threaded engines. We talked about what causes race conditions and how to deal with those using a mutex or spinlock or an atomic. We talked about how to split your engine up so that it can be running multiple things at the same time, specifically using that job architecture. And then last, we talked about how if you can wait for the answer to an operation, then it can be effectively split off onto one of these job managers to really make use of this many cores that we now have available on a modern computer system. Okay, that's it for today. We'll be doing a lab on this, and I'll see you next time.